introduction. So, friends, today I'm going to introduce you to the world of cosmology. It's an area of sciences that, in some way, has Gulish mentioned, tries to answer the questions that humanity has been asking for since the ages. So, ever since humanity looked up, they saw this Milky Way, as you can see in my opening slide. Nowadays, you can't see it in places like big cities, but I can assure you if you go to Hanley, this picture was taken by Jiangchuk at Hanley and it's spectacular. So it shows you the splendor of what's out there away and on very large scales. So let's try to understand it a bit better. So I have a similar picture taken on a lake with the Milky Way, but the Milky Way is our own galaxy. The stars that you see in the Milky Way are within this island universe, as it was called about a century back. Okay, now let's look away from the Milky Way. You still see things there, but let's look at a dark spot where you don't see anything, right? And you peer with the best telescopes you have. So still a few years back, I used to show you the Hubble Deep Field, then the Ultra Hubble Deep Field, the Hubble Ultra Deep Field, and now, of course, we have the James Webb telescope showing you that in every little bit of the sky, if you peer deep enough, it's full of galaxies. Galaxies that are so far away that some of them appear to be, just forming. And then some of them are behind massive clusters of galaxies and are lensed, like some of these here. And some of these splodges are galaxies which are just, beginning to form. What you can see here visually is only a small subset of the number of galaxies that's in this little frame that James Webb telescope provided. So obviously, once I show you this, you'd like to understand uh, what's our place in all this? What is the universe for and what is it doing? Of course, those are deep philosophical questions. As scientists, we would like to present this as a physics problem of, given the universe that we see now, can we infer what its past was and what its future will be? So let's move to the kind of cosmology that I'm going to do, since many of you may not have encountered these large scales of sizes and masses. So in the story that I'm going to tell you, a galaxy like the one we are living in, Milky Way or the Andromeda Galaxy, picture is shown here of the Andromeda Galaxy. Typical sizes of these galaxies are huge. It takes light 30 to 300, thousand years to go from one side of the galaxy to the other. Okay, so it's not just light years, tens of light years, it's 100,000 light years. And the galaxy has 100 billion stars. Okay, some have more, some have less, but that's a typical number. So you can see that this is a mammoth thing. I mean, it's full of stars. Even if you take our sun is a very, kind of average star, it weighs in at 2 into 10 to a 30 kilograms, which is 2 followed by 30 zeros. And then you weigh it in kilograms. So it's a huge, massive object. Then there are 100 billion of them in this galaxy. The galaxy itself is an extremely massive object. And as I told you, that the sizes are all measured in kiloparsecs. In astronomy, we have quaint units. A kiloparsec is 3.26 light years. So, and light year, as you know, is the distance traveled by light in 1 year, right? And we use that a lot in science fictions that we see around us. So, how's the universe around us? So, suppose we were, we started with observational cosmology and started peering back and mapping out what's around us. This is a bubble around, I mean, not bubble, this is an area of sphere of radius 650 parsec. Okay. So parsec you have to multiply by 3.25 for that many light years. And if you look around us, you can see already the distribution of matter has a very marked orientation, structure. So it's not a uniform fuzz of matter around us. This is the solar neighborhood. This is, in cosmological terms, doesn't even count. This is within the galaxy, right? So let's go beyond the galaxy and peer back. And you will see that the universe is full of such galaxies. And these galaxies are not kept in some uniform pattern or uniformly, but they seem to have arranged themselves in very rich structures. And it's apparent from this picture, but let me run the video so that you can see. If you fly through the universe in some magic hyperspace drive, this is what you'll see. You'll see galaxies floating past you. But then you will notice that these galaxies are on chains of galaxies, and then there are clusters at the nodes of the chain, and we are heading towards one of them. You can see multiple galaxies in that part, and so on. So this is a rich, large-scale structure in the distribution of galaxies that we see around us. Okay, and this is the problem a physicist would be faced when one wants to understand the universe, because we know now the map of galaxies, of hundreds of billions of galaxies around us. So let me move forward and show you Atlas. And this is what we know of the universe. And you can see that now you can't plot really individual galaxies, but largely you can see that spongy distribution of galaxies. But you just take a typical box in that, and it's a large box. We are doing cosmology now. So it will be 100 million parsecs on the side. Okay. And so on that scale, if I were to plot all the galaxies, this is actually real data from a survey called 2-degree field, taken about 2 decades back. Okay. And even then, we had this very refined picture of what a cosmic neighborhood would look like in the universe. And it's pretty typical. If you go back here, you can, give me the benefit of doubt that if I put this box anywhere here, it would more or less look like this structure. Now, what you see here are galaxies. They are colored in the color that they emit in, but the gray thing is not really there. It is like the dark matter skeleton on which these galaxies rest. So this is just to highlight the overdensity much easily for you. Okay, and you can see that the scale is 326 million light years, right? So I've gone from 100 megaparsec and changed it to light years. Now, if you were to look at this cosmos, you would wonder, how do I explain this? This rich structure, each galaxy here, even if I treat them like a point particle, that's what we do in cosmology that I'm talking about, you would really be faced with an enormous problem that, a condensed matter physicist is looking at a distribution of some phase in some, material would be faced with. So it's something that we need to contend with. But we are physicists, and if you take the distribution of galaxies around you and don't worry about how far they are, but just where they're located on the sky, okay, you would see something that suggests to you what is the simplicity in the whole thing. The simplicity is, if you look at this, this is a survey from 1970s, Leak Observatory Survey. I like this because this is the second page of a very popular cosmology text that almost every cosmologist reads by Jim Peeble. And it is at one go telling you that this is the entire sky, the northern half and the southern half. There's a part which has been cut off because in those days you couldn't peer through our galaxy itself. So it's the galaxy, our own galaxy, that doesn't allow you to see through its plane. But nevertheless, it's very clear that at the 0th level, there is no direction which is calling out for attention. Yes, there is structure, but the structure doesn't look any markedly different in any direction. Okay, so it's a good starting assumption to say that the distribution of galaxies is the same in every direction of the sky. any direction in the sky, I just count up all the galaxies in a solid angle, I would find more or less the same number of galaxies. So, which means that I can think of the distribution of galaxies as statistically isotropic. So, we'll just use the word isotropic. So, on the average, in every direction, there are equal number of galaxies. The universe doesn't have any specific direction to preferred direction. Now, you go another step and say, why should this be so only around us? And this is something that is a bit philosophical because this is something that we learned from Copernicus when we realized that the Earth was not something special. We realized the Earth is just a planet going around like other planets of the solar system around the sun. So, similarly, we think our galaxy is one of many, many billion galaxies in the universe and nothing special. So if the distribution of galaxies appears isotropic to us, it must be the same for any observer on any distant galaxy anywhere in the universe. With this assumption, okay, a mathematical theorem tells you that isotropy around every point implies homogeneity, which means that the distribution of galaxies in the universe is on average statistically homogeneous. There is no region of the universe that's very different from the others in terms of distribution of matter. Okay, now this is something that I'm giving you based on observations. But when cosmology started very early. When Einstein proposed his, theory of gravitation, which is, also known as general relativity or Einsteinian gravity, there, within years of that, he also tried to understand what it would mean for the universe as a whole. And to make the problem tractable, he used something called the cosmological principle that early model building already used, which basically said, let us assume that there's a homogeneous distribution of matter in the universe. And that itself, while is the simplest problem that you can pose in GR, sprung big surprise. Okay, and let me get to that. Einstein's general relativity applied to a uniform distribution of matter on cosmic scales led to a smooth expanding universe. It could be expanding or contracting, but we know that our universe at this point is expanding. So let's not complicate matters and think of expanding universe. Now, you imagine a century back, this was really, really, really philosophically troubling. We were used to thinking of space and time being fixed, right? I mean, you have a clock which ticks, and then you have meter scales which measure out space. Einstein's special relativity told you space and time can mix, but general relativity told you that the universe, with this assumption of a homogeneous distribution, cannot be static. It has to be either expanding or contracting. And this troubled Einstein so much that he tried to fix the problem with something to call the cosmological constant. I'll get to that later. But nevertheless, this is the universe we live in. If you look at the lattice of points, what it is showing you is galaxies are moving apart from each other, right? I mean, what is happening is you can, in this picture, it's much clearer. It's not as if there's a center to this expansion and things are expanding out of a center. It's like a membrane on which you have put dots and you have stretched the membrane. You can stretch the membrane as much as you want. All that will happen is this spacing between the dots will increase. But if I'm sitting at a particular dot, it will appear to me that all other dots are moving away from me, right? But any other dot would see the same, right? And that's the difference between thinking of a universe as some kind of an explosion at one point and expansion all around it. Okay, and this is sometimes a bit misleading because in many serials they will on science or cosmology they'll sort of describe Big Bang with a big roar and things that's as if there was a bomb explosion. Nothing like that. It's just that the space is expanding in time. And that is because general relativity allows space-time to be dynamic. And Einstein's attempt to pose a problem of cosmology gave you these solutions. Okay. And these are called Friedman, Robertson, Walker, Lemaitre, Robertson, Walker models. And these are, as I'm emphasizing, built on a very simplifying assumption. Right? But that's enough because you don't want too many surprises by complicating your situation. Many of you would have heard of space-time diagrams. So we in cosmology and general relativity, when we are talking of space-time, we like to plot events that are happening as something happening at a particular time in space, at a particular location in space. And then you have a space-time diagram of events. So let's try to draw a space-time diagram from the side because the time is suppressed, so I can't draw a 3D thing, but I will show you what it would look like in space-time diagram. So all these triangles that you see are the galaxies. And as you see, as time takes, each galaxy seems to be going away from this central one. But if you go back to your previous picture, if I took another galaxy to be the central one, you will see the same picture. It's like, all around these sticks are coming out with these, galaxies moving along them. That's the space-time that we have of our universe. Okay. Then we use something which is very useful in general relativity, and this is Einstein's relativity also gave a big boon to physics in saying you can do physics in any coordinate system. So you try to go for the simplifying coordinate systems. What we will do is have every instant of time, let's choose this surface and we will just factor out the expansion factor, how much this expansion has happened from the spatial coordinates as well as from the time. Okay, the advantage you get there that the universe in terms of a space-time picture where technically this is called co-moving space and conformal time has a picture that is very familiar to all physicists. This space-time diagram, notionally resembles something that you get in special relativity. Okay. Only thing is the ticks which were equal in time earlier become unequal in conformal time, right? But that is a nice description because this kind of immediately unfolds some amazing, tools that we use in cosmology. Now I told you, we are looking at galaxies, millions and hundreds of millions of light years away, or even a billion light year away. How do we know? How do we measure distances? I of course cannot wait to send a light signal and wait for it to bounce back and measure the time, right? The entire lifetime of the Earth will be spent in doing that. But you see, light travels in this space-time along this red line, right? From here. Okay, so this is the trajectory of photons, and that makes life very easy to understand one effect that is crucial in cosmology. Okay, before that, let me also tell you quickly that, I have told you of a space expanding in time, uniform space expanding in time is the model of the universe. So you can see that the flat universe is like a ream of sheets, one stacked over the other, showing the universe at different times. But there can be sheets or there can be surfaces of negative curvature or positive curvature. Earlier, till about 2 decades back, this was a rich area of, we needed to worry about all three possibilities. But as I'll come to in soon, our observations have shown that our universe is simple. It is actually a flat sheet in space, which is stacking over each other. So the flat universe. So I will not refer to this anymore. But that also fixes the total density of the universe to be a characteristic density, okay, which I'll get to. And then we have equations that we can solve for this universe. And I can tell you, for universe that are spherical, like the sphere, they will expand up to a particular size and close down. The ones which are flat will follow this green line, where going far off in time, it will also essentially stop expanding. Then there are universes which will expand at a constant speed. And then there are universes which suddenly start accelerating. So the expansion rate increases in time. So it seems to be coming down, but then it goes up. It so happens that the universe that we now know we live in is this red curve. So the universe started from a Big Bang, notional Big Bang. I won't, you can ask me a question about Big Bang and I'll answer what our understanding is. But the universe is going to expand forever at an increasingly faster rate. This is the universe we inherit. So this is where we are, where all the curves meet. And these, all I wanted to tell you is the equations of cosmology are very simple. Okay. So now what allows us to look far into the universe? Now this is something called cosmological redshift. Remember the space-time diagram in conformal time and co-moving space? The galaxies were lined up on vertical lines like this, and the clocks were ticking here. And so now imagine I send a signal to this observer. What does it mean to send a signal? So if I send a light, then the light has a crest, say at every of these points. So the first crest reaches this observer here. The second crest reaches at the first tick of the clock here. And the next one reaches at the second tick. Now you realize here that you have encountered only one tick, whereas to the clock carried by the observer, there are already two ticks, right? So that means time seems to be dilated, right? So this observer will see that when, everything that is happening here is at half the speed at which things are, rate at which things are happening here. So for light, what it means is if I shine blue light from here to there, by the time it gets there, it could be red at half the frequency. Okay. So equal time events at distant galaxies appear time dilated. So frequency of light from a distant galaxy is scaled by the expansion. Okay. It is called redshift because the fact that light gets red also happens due to something called Doppler effect. If something is moving towards you, it appears bluer. If it's moving away from you, it appears redder. But unlike Doppler effect, this is an effect that comes just out of the expansion of space. So you can see how important the whole idea of expanding universe is. And that allows us to now use, so since if you look at this last tick here, I don't know whether you can see my pointer, but if you look at the leftmost guy, there for every tick of the distant galaxy, there are 2.5 ticks. And it's easy to imagine as you go further away, time will be more and more dilated. So you can look at the redshift of light from a distant galaxy and estimate its distance. And there is a constant that governs it, which is called the Hubble constant, which is essentially the expansion rate of the universe. Okay. And so this takes us back to the first understanding that the universe is expanding. That was from the view that Hubble had of measuring the frequency of light from distant galaxies. He could look very far. This is about a century back. He could look at only 2 megaparsecs away, about 6.5 million light years away. But the galaxies, their velocity inferred from this Doppler shift and their distances seem to line up on a straight line. He was a very bold guy, and he put a straight line through it and, expounded something which is now, ingrained in cosmology called Hubble's law, that the recession velocity of galaxies is proportional to the distance. Okay, at the redshift, it's proportional to the distance. Of course, now we have much better measurements. I should have had a much more recent one, but you can see we can look further away up to almost a giga light years away. And, we see that the Hubble's law is fairly well obeyed. Okay. Now let's again look at another consequence of this expanding universe. So now you have galaxies in a part of the universe. So let's draw an imaginary box around the galaxies in one part of the universe. Now, if I look at some time back, this distances between galaxies would have been half. So essentially, this box would have become half its size. So number of galaxies density would go up by a factor of 8. Similarly, when the box is 1/4 the size, the number density would be 64. Okay. But there's a big difference between these galaxies, counting galaxies as amount of energy in the box. But if you had radiation in the universe, which was smooth and everywhere, that radiation would behave a bit differently. Number of photons, which are quanta of radiation, of course, will have the same relation as the galaxy. So when the universe is half its size, the number density is 8, 1/4, it's 64. But the energy density is grows faster. That's because you see the wavelength of light is also shrinking by a factor of 2, which means the frequency is going up by a factor of 2. And you know that there's Planck's law, which tells you energy is proportional to frequency. Energy of a photon is proportional to frequency. So higher the frequency, higher is the energy of the photon. So energy density of the photons rises as the fourth power of the size, whereas this one rises as the third power of the size. So if you think about it, at this time, even if this radiation background is very, very weak compared to the energy in galaxies, you just take the mass of the galaxy and multiply it by c square. MC square will give you the energy contained in there. And then if you compare, even if it is 10,000 times smaller now, when the universe was 10,000 times smaller in size, the radiation density of the universe will be the same as the matter density, which is the galaxies. So this leads us to an immensely important conclusion that in understanding our universe, we don't have to worry about everything. You have galaxies in patterns and all that. But the early universe is totally dominated by radiation. Okay, early universe, when the universe was 10,000 times smaller than what it is now, and even beyond that, everything is radiation dominated. So that's a simplicity. Okay, I don't want to go through these, but I also want to assure you that there are very simple, nice differential equations that underlie all this. It gives you various relations, and for different kind of matter in the universe, you can actually predict how the density scales. Like I told you, for radiation, it was 1 over the size to the power of fourth, whereas for matter, it was 1 over cube. These can be all worked out through physics equations. Okay, so I'm just wanted to assure you of that. And cosmologists are extremely imaginative people. So we have relativistic things like radiation, which scale as 1 over 4, the L4. Then you have pressureless dust, which scales as 1 over cube. But then the curvature of the universe also almost behaves like a 1 over square thing. And we also have something called vacuum energy, which we have just discovered 2 decades back, 2.5 decades back. And that is strange. That doesn't scale with the size of the universe, and so on. So, given any matter that you can think of that inhabits the universe, we have the equations to solve for what the universe will be like. Okay. Physics, we can build the entire picture of cosmic history. So, this is the universe at the rightmost. You see the universe now, the glass scale structure that I showed you. And then going back, you will get to hotter and hotter universes with different things happening until you get to a point where the universe just began. And this large expansion here is something that has been added in the last 40 years called inflation. But this is our overall understanding of the universe. But what I wanted to emphasize that right up to this part, which is shown in gray at the end, where this curve, everything that we know is based on very basic physics. So up to 10 to the power minus uh, 30 seconds, or maybe 20 seconds, every physics that we use is fairly well defined. Okay, and it's lab tested. Now, since I told you where that the universe is radiation dominated, now you can ask, is there such a radiation background in the universe? If so, where is it? Okay, and amazingly, nature has been very kind to provide us a band in which we can detect this radiation right at its peak. Okay, the cosmic microwave background are photons that arrive to Earth from every direction that you can look at. So they were discovered when one of the early radio antenna was being calibrated, and they couldn't get rid of a noise because that seemed to be there all the time in every direction of the sky. But then that is the relic glow of the early hot universe. Okay, and at this time, this follows an extremely tight fit to a black body, like a pure black body radiation. So it's just characterized by the temperature, and so the entire radiation content of the universe is characterized by one single number, which we can measure nowadays to the third decimal point. But I'll just keep calling it at about 3 Kelvin, right? And the important thing we learned is this, from 65 to about 92, as far as we could judge from the more sensitive and sensitive measurements, there didn't seem to be any differences in the temperature at different directions of the sky. So up to 10 parts per million, the sky appears extremely smooth in this cosmic microwave background. Okay, and that is the strongest support we have for the model that we have used for cosmology, which is that the universe is isotropic around us. And if it's isotropic around us, it must be isotropic around everyone. Hence, it's a homogeneous distribution of matter. So although matter, it is clear, but you might argue about it. In radiation, to, 10 parts per million, there's no question that the universe was homogeneous in the past. And this also tells you that there was a hot phase in the universe. I won't really get into that, but because of this importance of this discovery, this was given a Nobel Prize in 78. And our understanding is the following. So I told you this conformal time and space diagram. So there I told you light travels around this 45-degree cone. But what we are seeing here is, as I go back, I see an earlier universe, and I go back to a time when the universe was 1100 times smaller than what it is now. So then the temperature of the microwave background, instead of being 3 Kelvin, was 3300 Kelvin. Okay, so it's a glowing plasma that is there at the end of this. But this also puts a limit to looking at the universe beyond this point. Because it's a plasma, it's sort of everything that is happening before it is kind of hidden from us, just like a fog hides everything behind it. It's the same phenomenon. It's like a cosmic fog that surrounds it. So let me give you a picture which is much easier to carry home. So we are at in a universe which is about 14 billion years old here and now. As I look out to further galaxies, I can only look through light. So I'm also seeing the universe as it was in the past. So it's a natural time machine in which the universe reveals itself as we peer further and further into the universe. And the microwave background, cosmic microwave background, is somewhat unique because it is the furthest we can look out with light in the universe. This is an absolute limit. And this limit comes like around every observer in the universe. You have a plasma screen placed naturally by nature. It's all around us. So imagine a sphere which is glowing. and it's 43 billion light years away, so you don't worry about it. It's at 3,300 Kelvin. But the expansion of the universe makes sure that the light that is coming from that has cooled down to 3 Kelvin by the time it's come here. It's the cosmological background. And the reason it is isotropic is because the universe is so homogeneous that the microwave background from any point on this sphere, on the plasma surface, is more or less the same. Of course, this was exciting. And I should also point out that it's very interesting that the universe is transparent at these wave bands. It need not have been so, right? So we are really, really fortunate to be able to peer back to the furthest distance that you can peer back with light, right? Now, with the microwave background, what you have is essentially a super IMAX theater. It's sort of displaying the universe as it was when it was only 500 million years old. Now the universe is 14 billion years old. Right? That's like looking at a one-day child, relative to a 100-year-old self, right? So your picture when you are old. And then the other thing to notice is that, till 92, you would have got over all the excitement and started wondering, is there anything more? Okay. And in 1992, essentially, there's this cosmic background explorer, a satellite sent by NASA, which discovered tiny fluctuations in the temperature of the microwave. So it's not that they appeared suddenly, it was always there, but we didn't have the sensibility to measure these fluctuations, which were at 10 parts per million. And that was immensely important because, as I showed you in my opening slides, the universe we see now in galaxies is not totally uniform. On the average, yes, things are fine, but there are structures, and this gives you a hint that the universe was 500 million years old. Already, the plasma had density perturbations, fluctuations on it. And it's a rich plasma physics, but very basic plasma physics that you can use to understand this. Okay. And then this sort of immediately tells you that there was a hot, dense universe in the early times. The universe was at least 30 million kelvins hot just because of this black body curve. And then we also are faced with this question of these structures giving rise to the galaxies. But it's a well-defined problem. In physics, we love problems where the initial condition and the final condition is given. And we have some idea of the dynamics, but we need to know the parameters, like how much of friction. So suppose you know that a ball, came down an inclined plane. If I give you the initial velocity and the final velocity, many of you will be able to work out the entire dynamics of this ball. But then maybe you have to worry about friction, you have to worry about things. Something similar here. We know what the universe was like when it was 500,000 years old. We know how the universe is now. We see this in radiation, we see this in matter distribution. And we have an understanding that small fluctuations in gravity get amplified because of gravitational instability. This is not new. Even Newton knew that there was this problem that if the universe was fully homogeneous, then a small perturbation there will grow uncontrollably. But what he didn't know is that the universe is expanding. So it doesn't grow as fast as it would have if the universe was not expanding. Okay. But nevertheless, there's enough time to grow these fluctuations at 10 parts per million to this rich last-state structure. And that's what we have been doing. The other part which we seek to do next is to look at the origin of this fluctuation. So it's like I'm seeing the IMAX theater, it's showing some interesting picture to me. But someone has drawn this picture, and we think it's some high energy physics phenomena that we have still not uncovered. And I will mention these two parts of our current understanding of the universe. Okay. So again, just for you to know, the temperature of the microwave background is about 3 Kelvin. The fluctuations are 10 parts per million. So it's about, tens of microkelvin. And then there are polarization patterns, which I'm not going to cover in this talk. Now, let me say that given such a wonderful super IMAX theater, obviously you would like to exhaust all the information that we can measure out of it. So while Kobe discovered that there was some variations in the temperature, it didn't have the angular resolution to resolve them very well. So it was like this blurry picture with, it's just like someone looking through thick glasses, like someone like me. Okay. But in the next decade, NASA sent out another satellite called the Wilkinson Microwave Anisotropic Probe, which gave you a much more refined picture of this IMAX theater on the IMAX theater, being played on the IMAX theater. Gave you in better detail what the fluctuations look like. And finally, in the following decade, there was a satellite from the European Space Agency, which really mapped out a lot of the temperature and fluctuations on this. And this game is going on, right? So Planck almost exhausted all the information, temperature, but there's a lot more to get. And I should also mention, although people marked these decades with these 3 space missions, there were equally large and important efforts from ground-based observatories. And this effort is still going on. So what is the state of the art in our field, Planck, has been surpassed on the ground by many, many experiments which are now running in South Pole. So you are in the 2020s here, right? So let's now focus on the best maps we have of this IMAX theater. So this is the map of the entire sky. Okay, so we in astronomy love to represent the entire sky. You can't create globes everywhere, right? So just like geophysicists or geographers, put the map of the Earth onto some kind of a projection. We put it on a projection where the whole sky is seen here, and you can see the exquisite detail in which we can see the fluctuations of the temperature on this. Okay, and this is amazing. Now, what we are really concerned with is, I know that there is no direction to it. So there's no point in saying, oh, let me orient the map this way or that way. It's more or less going to give the same information. And it's a random map in the sense that we don't think there is any pattern in it. So what you do in such things, just like if I have a table and I want to measure its roughness, I assume that any patch of the table I measure the roughness, that will be reflective of that. So I measure it in terms of root mean square of the roughness that I measure on a patch. I can do that on multiple patches and be happy. But now suppose you have roughness and different scale. So on tiny scales, maybe the roughness is at tens of microns. But on centimeter scales, it's at a millimeter scale and on the scale. So then this is what is happening here. On different angular scales, the temperature fluctuation has differences. And that is due to the resonant phenomena of a plasma screen. So we understand it very well. And we can predict what the fluctuation spectrum would look like in a given cosmological model. And we have amazingly great measurements from Planck of this power spectrum, right down from the scales of the entire sky to about tens of arc-minute scale. All around this angular scale, this is the inverse angular scale shown here. And you can see that the measurements are exquisite. You can hardly see the error bars in most of them. And you have to subtract the red curve from the measurements to do that. Now, look at the great situation we are in cosmology. So we have a curve that I can draw. If you tell me what you want to put in the universe, the mix, you want to say, oh, the universe has so much of ordinary matter, so much of cold dark matter, Hubble constant, expansion rate, things like that. You give me a recipe in this isotropic and homogeneous universe, I can immediately draw for you this gray curve. And then what I can do is keep varying these parameters and try to look for a combination of parameters at which this gray curve totally threads the green measurements from Planck. And this is something called Markov chain Monte Carlo. It's a standard technique, and this is done by my student for me. And you can see soon you settle down, and there is only one particular curve that will really match all the data points. And then you can read off what is the cold dark matter density of the universe, the ordinary matter, the expansion rate. These parameters tell you the characteristics of the universe. Okay? And this is very reliable because this gray curve is based on very well understood physics of resonant phenomena in a plasma. So there is nothing really fancy about the physics used here. And using such physics, cosmology is at a epoch very different from what it was when I started my research in early 90s. When the Cosmic Background Explorer came out, I was one of the first people to work on it from India on that. And then there we knew some of these numbers to really large uncertainties. This constant of expansion rate, Hubble constant, was known to a factor of 2. Now you see, we know things like the ordinary matter density to a percent level, whole dark matter to 2% level, and so on, right? Explicit measurements. And that tells us that we can finally say, we can put a strawman model. We can say there's a standard cosmological model, which is simple, it's spatially flat, it has to have vacuum energy, it has to have cold dark matter, and a little bit of ordinary matter. And that fits 6 parameters, fit everything that we see in the microwave sky and also in other cosmology. But the cosmic content is very, very surprising. So if you look at the pie chart on the left, the black one, we see most of the energy density of the universe is in a form which we don't recognize. So we call it dark energy. Then we have 25% in a form which we call dark matter. Now, both are dark because they don't interact with electromagnetism or light. So they don't absorb or emit light, so you can't see them in astronomy. Okay. The ordinary matter that we know of, protons, neutrons, everything in particle physics that we know of, constitutes only 5% of the energy density of the universe. So if we were not humbled by the fact that we have one ordinary galaxy in 100 billion galaxies around us, this is humbling that whatever we know till now about the content of the universe accounts for only 5%. And that 5% itself is spread into various things. Stars that we see are only 7% of the 5%. So you have to multiply the two, percentages to get how little stars count in the universe. On the cosmic scales, these things that we hold dear to ourselves are really a minor player in the dynamics of the universe. Okay. So what has happened? We started off with a very simple assumption, okay, and which has been borne out very carefully with a lot of observations, that the universe is on the average homogeneous, the matter distribution homogeneous. Then we found that the radiation density is observationally shown to be extremely uniform when the universe was only 500,000 years old. Okay. And then if you build that cosmology and use all basic physics to say what is the universe, it's a very exotic universe. 95% of the energy of the universe is in some exotic form, which we yet have to discover. So there's dark matter. We cannot see it directly, but we know its presence because of it gravitationally clusters. It also bends light, gravitational lensing. Dark energy is a smooth form of energy which resists gravitational clustering. But we need to have both of them in the ratio of 70% of dark energy, 25% of dark matter, and 5% of ordinary matter. Okay? And importantly, since we have inferred all this from the fluctuations imprinted on this plasma screen, we also know something must have caused those fluctuations in the first place. And there is some ultra high energy physics that we need to still understand for generating these fluctuations in the first place. Okay, so the question is, who pinged the cosmic drum? If you imagine the universe, the spatial surfaces to be some kind of a magic membrane of a drum, then this drum is actually been hit, and it's resonating with some vibrations. Who caused that? So our best guess is that these were caused by quantum fluctuations in the very early universe, when the universe had a phase called inflation, where it had an extremely rapid expansion, accelerated expansion, for a very brief period of time. But that is enough to explain the universe we see now, and as well as explain what these fluctuations are. So again, in this era when we are talking about national mission on quantum technology and applications, quantum mechanics applies on the grandest scales of our universe. Okay, we believe every structure that you see in the universe arose from quantum fluctuation in the early universe. Now, of course, this is a big claim, and we need to be sure about it. Till now, amazingly enough, detailed measurements of this cosmomicro background and other observations of cosmology are consistent with the predictions of this inflation, right? And this has some particle physics aspect to it, which we don't know yet. So this is a challenge for particle theorists, physicists to come up with an idea. But there is still one thing that we want to measure before we are totally sure. Now, what is interesting is a mechanism by which I said all the structures, these seed perturbations that we see in the microwave background, were generated from quantum mechanics of the early universe. That quantum mechanics would have also created gravitational waves. This is something that we can't escape. Only thing is you can vary the amount of gravitational waves relative to the density fluctuations in different models of inflation. And that is given by something called R, which also tells you the energy scale at which this physics must operate. And at this point, we have upper limits on that. But to measure this number, not just put an upper limit, is a must do or to do for cosmology. I mean, we need to do this because then that will complete the picture for us as a physicist, how well we understand the origin and evolution of the universe. Okay. So to that end, what is required for a primordial gravitational wave discovery is a near ultimate CMB polarization survey. So we have measured temperature fluctuations very well. We also have measured polarization of the CMB to some extent. I didn't talk about the polarization of the CMB, but the photons are linearly polarized in every direction, and that has extra information. Okay. The ultra high payoff of such a survey would be that it will reveal the signatures of quantum gravity and ultra high energy physics in the very early universe. So because it will see signatures of gravitational waves of quantum origin. They arose through the quantum phenomena that gave rise to all structures in the universe. They also gave rise to gravitational waves. Note that this is a LIGO detection, we only see classical gravitational waves. So this will be a great boost for our understanding of quantum gravity. So given this high, ultra high, possibility, we often forget that any effort on this side would have huge payoffs, which are very important: neutrino physics, etc., dark matter, ordinary matter. And then this is, of course, unexpected discovery space moment we push the capabilities of our observations. But this is what we wanted to do. So I just wanted to end by saying that we did put a proposal to ISRO when they had a call for proposals a few years back. And this was by an Indian Cosmology Consortium. We would like to send a satellite to do this next generation measurement of the cosmic microwave background. It is some information waiting to be mapped out, and we must do it. Someone must do it in the world. And we hope to inspire ISRO to take lead and bring other players on board to send a satellite which will be as large as Planck. So it is about 4.4 meters in diameter, 4 meters in height, That fits within a GSLV Mark III, which is, which is the one which launched Chandrayaan. And then it will go from Earth to the second Lagrange point. If you know, the second Lagrange point is where James Webb Telescope is, and another amazing cosmological observatory called Euclid is heading there. That's a wonderful place to map the universe, because you can look away from the sun and the earth and moon, all the contaminating things, and you can look away and keep mapping the universe at high resolution. So I'll end here by, my cosmology talk saying cosmology is yet to reveal amazing things. And this is also borne out by the Nobel Prize lectures, if you may hear them, of the gravitational waves of the discovery by Kip Thorne and Rihanna Weiss. Both mention the next big thing scientifically would be the measurement of primordial gravitational waves from the origin of the universe. So this is what I hope, that we will at some point take up this opportunity to take lead on a prize quest in fundamental sciences. Thank you.